Our next presenter is the chairman of the HPCAI Advisory Council, Gilad Shainer, will be giving us an overview of the latest in terms of supercomputing architectures and what's happening with cloud-native supercomputing.
Love when magic works. By the way, fascinating presentation. Really fascinating presentation. So kind of switching areas and moving from an applications perspective to look into the infrastructure of supercomputing, and we are excited to be part of several organizations that exploring or creating capabilities of actually enabling the next generation of infrastructures or the next generations of platforms that can bring new capabilities into supercomputing, which is another exciting area. So I'm going to start with a little bit of history and how things moving forward, and we'll talk about what's happening from a cloud-native supercomputing. Cloud-native becomes an interesting concept. Everything becomes cloud-native, and it's also goes into supercomputing. So if you're looking, several years back, traditional supercomputer, storage, computing elements, and then the network infrastructure that connects everything together, latencies were high, and if the network latency is high, then the framework, HPC frameworks latencies is high, and then the CPUs or the computing elements needed to speed their time, part on the compute element and part of the managing of the communications area, which was kind of half and half or 50-50. And then RDMA was created, and RDMA enabled the network to actually migrate the transport management and the network operations into the network, so the network managed that part, and moving that or offloading that from the CPU or any other compute element, and that it reduces the utilization of the CPU or increase the time that the CPU can allocate to the computational elements. RDMA also reduces the latencies, so it was great to see ping latency goes down. But when we looked on communication frameworks, if it's MPI, SHMEM, PGAS, UPC, you name it, latencies there were still kind of high because there is much beyond of the ping latency. Right? You reduce the ping latency to be extremely low, but still there is more of the complicated or complex operations of frameworks that their latency was still high. So with RDMA, we can move data directly from the network to the user space. And in that case, and here I'm using some of the VApid team testing results. There is RDMA that moves data from the network to directly to the CPU memory. And of course, there is a GPU direct RDMA that does the same thing, but moving data directly from the network to the GPU memory. And now there is also GPU direct storage, which does the same thing. So there is a variety of elements that use RDMA. And from a GPU direct RDMA perspective, just taking one example, using RDMA reduces the latency of moving data to the GPU memory by around 10x, and then improve the throughput of moving data between remote GPUs that sits on remote platforms by an average of 10x. I think it was like 9x for unidirectional, 11x for bidirectional. So in average, it's a 10x increase in bandwidth capabilities. So then looking on the next step, and the next step was introducing of what is being called in-network computing. So beyond of migrating the network operations to be managed by the network itself, and then bringing RDMA to reduce ping latencies. The next step was bringing in-network computing capabilities, which are computing engines that are natively part of the network elements that can help with migrating the communication framework operations to be executed on the network. And the idea behind that was that ping latency is nice because it's for ping pong operation, it reduced latency, or send receive in that sense. But when we're looking on collective operations, it's a different story. And by introducing the in-network computing capabilities, you can actually start to migrate more of the complex communication operations and run them on the network, which is essentially a more ideal place for those operations to be executed. And that's from the reason that the network is much more immune to system noise and jitter. With a few devices, you can actually map a very large infrastructure, which means it scales much better. In that case, it can give you flat latencies for complex operations. And one example for in-network computing capability that provide a great advancements or performance advancements for communication frameworks is what's called SHARP, or Scalable Hierarchical Aggregation and Reduction Protocol, which in short is the technology that enables to migrate data reduction operations to run completely on the network. And with that technology, instead of doing an all-reduce operation or barrier broadcast, for example, on the CPU or in a GPU perspective, which requires to move data to that specific compute engine, all of the processes just send data to the network, and then the network can do the data reductions on different tiers, depends on the system size, and then also do a broadcast of the result back to the hosts. That gives flat latencies, as the network is much more immune to the system size, and of course much lower latency compares to doing the same thing on a CPU. And there are several other side effects, for example, reducing data motion, which is also a great thing, and more. Now, just to illustrate the benefit of that and why the network is a more ideal place for the reduction operation to be executed on, is we can just take an example of a three-level fat tree network and multiple nodes. And then we can look on what we would do in a traditional way. And in traditional way to do data reduction and multiple hosts, it will go through several iterations. And this is example. You can have other implementation examples, of course. In this case, in the first step, all pairs of nodes will exchange data between themselves. And post that iteration, for example, node number 1 will have the data from node number 2, and node number 2 will have the data from node number 1, and so forth for the rest of the nodes. Then we'll go to a second iteration where node number 1 will exchange the data that it has, which includes the data from node number 1 and the node number 2, exchange it with node number 3, and node number 3 will exchange the data with node number 1. So after this iteration, all the 4 pairs, 1, 2, 3, and 4, will have the same information, and then the same thing for node 5, 6, 7, and 8. And then, of course, we need to go to the third iteration, in which now the 2 groups will exchange data between themselves. And at the end of the third iteration, all of the nodes have the data from all the rest of the nodes, and this operation is pretty much done. So we need to go through 3 iterations, which took long time compared to other things. And of course, there was a lot of data exchange between the nodes, or between the hosts, or between the processes. In a SHARP scenario, when you migrate the data reductions to be executed on the network, In this case, all of the nodes will just send the data to the switch devices. Switch devices do the data aggregation, move the results to the next tier of switches, which do the reduction among the groups, and then it goes to the top level of the reduction tree that completes the reduction operation, and then the data flows back. So first, can be done much faster, and of course, the second, there is much less data that needs to be exchanged between the hosts, and that's why there is much less data motion, less congestion, and so forth. And there is no CPU latency additions as what we see when we're running everything on a host. So that's the benefit of in-network computing. And Sharp is one example, but there is other engines that are part of the network today that can do further operations, such as doing matching. And by doing matching on the network, you reduce the system noise, obviously. You increase overlapping capabilities. And by doing that, you can actually migrate the entire rendezvous protocol to be executed on the network. So those are examples of where you can utilize, or where we utilize in-network computing in order to reduce the communication frameworks latencies, or the more complex operations of communication frameworks latency, to reduce that latency. Now the next thing is to bring security into supercomputing. And I think the last year of COVID-19 actually demonstrated why security is important. There were multiple cases of supercomputers that were tampered to run applications that were not supposed to run on those supercomputers, and that demonstrate the need of bringing security into supercomputing. And bringing security into supercomputing means that a supercomputing becomes something that starts to look more from a multi-tenant environment, or a cloud environment in that sense. Now, today when we build supercomputers, obviously the most important element is performance. And the more performance you have, the more things you can do with that. Now, adding security capabilities, for example, or adding multi-tenancy support, isolation between users, means that there is an extra overhead that will take place, which means that the performance of the system will be reduced. Now, on the other side, when we look on cloud infrastructures, in a cloud infrastructure, there is a great security. It supports multi-tenancies. It needs to isolate users, isolate between jobs, and so forth. But you don't really gain bare metal performance, or you don't really gain the maximum performance there. So this is where you can. This is where there is some conflict, and the question is, how can we bring security into supercomputing while maintaining bare metal performance? And the way to do that was actually utilizing a new concept of devices, and new networking devices that start to exist in the market, which are being referred as data processing units, or DPUs. Those devices brings all of the network capabilities, but not just the network capabilities from a network adapter perspective, but they also includes computing engines, programmable computing engines on the same network device. So if on the in-network computing subject, we refer to engines that were designed to do something very specific, here when we're looking on a DPU device, these computing engines are actually completely programmable. And I'm taking an example of one of the devices that exists in the market, where the programmable devices are ARM cores, which mean you run Linux on that network device. And when you have the network, this device as a network adapter in a server box, you actually have a Linux machine within a Linux machine. And that Linux machine sits close to the network. It's detached. It's not connected to the host in the sense that the CPU on the host, when you're doing all the security initialization on that device, this device also runs the applications. This device also hosts the users. And this is a reason for some of the probably security glitches. But here, you have another CPU or DPU that sits on a trusted domain. It's not the same domain that hosts users or hosts applications, which means you can actually increase security by using this device. But that's kind of a side note. Now, by having another Linux machine within a Linux machine, which is not related to where you run the application side, you can actually migrate a lot of the infrastructure management from the host and run those services on a DPU, which means that if previously I run, or if a cloud environment, I run my multi-tenancy and isolations on a CPU, now I can actually do the same thing on a DPU, and that means that I'm not putting any overhead on a CPU, which means I can get to a bare metal performance. So this is kind of the quote-unquote secret sauce of enabling security for or in supercomputers by not using the CPU, which will reduce the system performance, but by using the DPU, which can manage the management, the isolation, and even do more. Because now you, with the extra compute, or with the compute that sits on a trusted device, you can also migrate file system management into the network or into the DPU. If it's network file system or cluster file system, for example, and that further reduce overheads and actually bring more security capabilities. So those devices, the DPU devices, helps to move a supercomputer, a classical supercomputer, to a cloud native supercomputer, where you keep bare metal performance and you also enable multi-tenancy, which means you have you bring isolation between jobs, and that's kind of moving supercomputers towards a zero trust data center architecture. Now, it's not just isolation between jobs, it can also bring isolation or performance isolation. So one of the things that we need to, or tackling in today's supercomputer is that one job can reduce performance of another job because that accessing, for example, a common storage environment, and one process takes more of the storage capacity, and then there's less capability available for another process, and this is where when one process can reduce performance of another one. So the DPU devices can bring or enable isolations between users or tenants or jobs, but also bring performance isolation, which is another great thing. So that's where we see the infrastructure moving towards, and moving towards a cloud native supercomputing approach. There are software capabilities or platforms that are being developed for that. And here I'm reusing an architecture view of one of the software capabilities or some of the SDKs being developed. And again, the idea is moving management, isolations, monitoring, file system services, and instead of running that on the host, doing the same thing and running that on a DPU, which sits in a trusted domain. So by doing that, the job or the user or the tenants stays, or quote unquote, locked on the host itself and has no control of the resources outside of that node. The DPU provides all of the services to the node. The DPU is the one that controls access to storage, for example, and then the tenant or the job actually mounts storage on the DPU, and then the DPU does the same things on the storage, and you can control the storage access. So with that, again, you keep the bare metal performance on one side because there is no overhead on a CPU, there is no overhead on a GPU, there is no overhead on any other compute device that is being used to run the job, and everything there, it actually runs on the DPU. Now, if we now includes DPUs in every server, then beyond of migrating the infrastructure management or the infrastructure services to the DPU, now we actually have more compute capacity. Which sits closer to the network, which means that we can also use that for increasing performance. And thinking about creating a hybrid model of a CPU and a DPU, which they can both participate in process runtime, or even creating a hybrid of a GPU, a CPU, and a DPU, or any other compute combinations. So now with the extra capabilities there, you can think about doing for-their accelerations for collective operations. So for example, if a reduction operation, which is all reduced barrier broadcast, could run on a dedicated engine on the network, some other collectives actually can run on the DPU cores, and with that achieve overlapping. And with overlapping, you also reduce latencies and you can increase performance. You can think about utilizing active messages or using the DPU for MPI progression, which will improve the capabilities of send receive, compressions, and many other user-defined or specific job-defined algorithms. One of the elements that was done recently, and I think it's also presented this week in some other places, and obviously we'll see more presentations around that. That's a work that is being done by the VApid team from the Ohio State University, which developing VApid to be able to utilize a hybrid model of a CPU and a DPU. And what they've done is that they're using the DPU to migrate asynchronous all-to-all operations to the DPU and actually pipeline the all-to-all operations into the DPU, and if the DPU runs those operations in parallel of CPU advancing or continue with the computational side of things. By migrating or pipelining all-to-all operations into the DPU, the overlapping capabilities for MPI all-to-all increase from almost 0% to 100%. And you get the full overlapping, and then by taking the three-dimensional FFT and modifying the three-dimensional FFT to use asynchronous all-to-all, they were able to demonstrate 30% performance increase for FFT, which is a great example of how in a hybrid model, where you pipeline more of the operations, more of the computational operations to run on the DPU in parallel of increasing the compute capabilities on a CPU, enables to not just enables to bring actually increase performance of supercomputers. So the DPU, it's a great element that now being added into supercomputers, which brings security. I think it's probably we're bringing for the first time, or that DPU enables to bring for the first time security into supercomputing. So maintaining bare metal performance and enabling isolation, user isolations and performance isolation. And the other thing, it's enabled to further increase performance. And a 30% performance increase for FFT, it's a great example. And I'm sure that there is other elements that will be developed throughout the HPC community over time, which will be able to leverage the hybrid model between the host computing engines and the DPU. Beyond of doing those developments by the different parties, there is also an effort done by the UCF consortium, the Unified communication UCF consortium, which manage multiple projects. UCX, if people are using UCX, is being managed or developed by the UCF consortium. UCC, so if UCX is dealing with point-to-point, UCC, it's another project of UCF, which is doing the same work for collectives. And there is another project, there are several other projects, but the one that's relevant, it's called OpenSnappy, which develops an open source API for applications to access the computing capabilities on the network in a standard way. So OpenSnappy enabled to expose capabilities of DPUs, for example, and potentially other computing engines that now we start getting on the network to the applications. So that's an interesting project, and I do advise you to check it out, and it's part of the UCF consortium. So with that, I want to thank you, and then hopefully you are excited as we do to see a new development that comes from an infrastructure perspective that brings more programmable computing into network components, how the SDKs are being created, the interfaces are being created, standard interfaces are being created, and then what that can bring to supercomputers. First, security and isolations will become more and more important, keeping bare metal performance, and obviously be able to improve performance of supercomputers. So with that, I think I'm running out of time, and therefore I would like to thank you very much for listening.
Thank you, Gilad. I do have a few questions for you, so let's go ahead and start with them. The first one is, do you think it would make sense for processor vendors to add in-network reduction for the network used to connect multiple cores in a multi-core processor?
Yeah, I'm trying to. It makes first on the networking side of things, we're seeing more computing capabilities being added, right? So there's the in-network computing engines, which refers to dedicated engines for a specific task. And then we see programmable engines being added, which enables to migrate different kind of operations and enabling services to migrate from the CPU to the network. Now, the reason that it's running on the network. So the question is, does it make sense from a CPU perspective to add multi-process reductions to run on the CPU? The answer, it doesn't really make sense, because if you look on reductions, the optimal place for reductions in the network and not on the host, regardless if it's a CPU or whatever. Because if you do a multi-process reductions on a CPU, that means that you need to actually move data from every place around the network to that specific CPU or to multiple CPU to do the reduction. And actually, the network is an ideal situation, an ideal place, because you move the data from all of the nodes into the network, which connects to everything, and then the network can do it in one iteration, or virtually one iteration. That's why it doesn't make sense to run that a multi-process reduction on a CPU. Doesn't make sense. It will not save the data iterations across all the multiple services around the system. So there is algorithm. Oh, one step back. If you have computing on every device in a data center on a supercomputer, it enables you to define what is the optimal place for running a specific algorithm. So reduction, the optimal place is to run it in an entity that connects to all of the nodes, all of the processes together, and that's why it makes sense to run it on a network and not on a process, not on a CPU. Does it make sense to run it on a CPU?
Okay. Thank you. Next question is, in terms of the systems you are familiar with, how much of the power of a node is consumed by a DPU?
Yeah, obviously a DPU consumes more power than a network adapter that does not include those computing engines. So in the case that I showed was some ARM cores on that. So it does take more, but on the other side, those are ARM cores, and they're not as compute or power hungry as what you see on a x86, for example. So there is some extra power, not as a CPU, much less. On the other side, this is a DPU is a place where it's isolated from the applications. And that's why if you bring security, you can actually go to a zero trust infrastructure. And then if you are achieving 30% more performance on a data center, on an FFT, it completely makes sense. So there is some extra, but it's not that much as far as I remember. And obviously there is numbers that are presented by different vendors.
Okay. And what do you think is going to happen first? Cloud providers with bare metal-like performance, or on-prem providing cloud-like security and access?
Well, I think the DPUs actually have both. So today on a cloud infrastructure, you lose performance capabilities because you're doing all the isolations and security and the rest of the things on CPUs. Now, user don't see those CPUs, but the cloud vendor does see that CPUs, right? So it could provide much better capabilities, but they need to run the infrastructure isolation there. And then on-prem system, if you look on supercomputers, you can get best performance, but isolation is not there. So I think the DPUs actually have both. And we'll see DPUs in the cloud, we'll see DPUs on-premise, and on the cloud, they will be able to improve the performance capabilities, and on-premise, they will be able to bring isolations and security into supercomputers.
So your answer is that it's going to happen at the same time?
I think both are moving forward, and I do believe that we'll see multiple cloud-native supercomputers being built this year, on-premise or the cloud, but we'll see, and I think it's going to happen both. I think we're going to see both.
Okay, and going back to the in-network computing and multi-core processor question, should there be in-network computing in the network for used to connect the multiple cores in a multi-core processor, in addition to in-network computing in the network for connecting multiple nodes?
First, in-network computing is okay. I see that. First, on the network, in-network computing is a must in that sense, because when you're running multi-node operations, if you don't have in-network computing on the network, then you are not able to go to much lower latencies and reducing data motions and doing things much more effectively. So that's one thing. Now, in-network computing on a node means that instead of running operation on a shared memory between processes of a node, I can actually use in-network computing on a network device that sits in the node. And that's yes, it does make sense. And I'll give you one example of something that it doesn't make sense in the network is actually doing tag matching, on a node. And when you do tag matching on a network device that sits in the node, you actually save the CPU interrupts. And if you save the CPU interrupts, then you can increase performance of that. So we're seeing that doing that on the CPU itself, I'm not sure there is something extra to do that, but doing that on a network device on the node makes sense for some operations. And then doing that on the switch devices makes sense for different kind of operations.
Got it. Thank you.